So let's go over these exercises dealing with acid-base strength. So our first two questions, we're just looking to write the formulas for conjugate bases or conjugate acids. So recall that the conjugate base of an acid is just the result of what we get after an acid has lost its proton. So that means that something like our bicarbonate anion here will lose an H+, which means it will have one less hydrogen. And because that hydrogen that it lost was positively charged, its charge will also go down by one or become one more negative. So the correct conjugate base for the bicarbonate is the carbonate ion. Here with acetic acid, again, it loses specifically this proton. As we'll see in the future, it's much easier to lose hydrogens that are on oxygen or nitrogen than it is to lose them on carbon. The reason for that is that oxygen, being more electronegative than carbon, is able to better support the negative charge than carbon can. Alright, if we're doing conjugate acids, as we are in question 2, we're going in the opposite direction. So we're adding an H+. So its conjugate acid here gets an extra hydrogen, and it adds a +1 charge to whatever charge it already had. This compound was neutral, so it becomes a charge of +1. Same thing with NH3. If we add an H+ to that, we get NH4. It was neutral, becomes positively charged. Alright, in question 3 now, we're trying to calculate the pKa for HCN given the Ka. And so recall this P, whether we're talking about pKa or pH, this P here basically means negative log. And so we take the negative log of the Ka. The Ka is something that's given. So negative log of 4.9 times 10 to the minus 10. And that's relatively straightforward to put into our calculator. And we get 9.31. One thing to be careful of, when you're doing calculations like this on your calculator is, when you're using scientific notation, you will often find either an E or an EE button, and those are what you should usually use for scientific notation. Sometimes if you type out this exactly the way it's written, 4.9 times 10 to the minus 10, some calculators will actually mess that up, especially if you don't put parentheses around that properly. Alright, question 4. Which one is a stronger acid, succinic acid or oxalic acid? And with the Ka's given, all we have to do is look at the Ka's. So what is a stronger acid, a smaller Ka or a larger Ka value? The larger the Ka value, the stronger the acid. And so because of that, of this pair, oxalic acid is the stronger acid. All right, question 5 here is very similar to the one that we ended the last set of lecture video with. And that's that we have H+ concentration of 1 times 10 to the minus 10 molar. and I want you to determine three things. What is pOH? What's the concentration of hydroxide? And is it acidic or basic? So as we saw, there's a lot of ways that we can go about doing this problem. All of which are essentially the same, just a different order of the steps. So the first thing I'm going to do is, we're not asked for it here, but I'm still going to calculate pH. So the pH is equal to the negative log of 1 times 10 to the minus 10 molar, because that's the concentration of H+, or pH of 10. So if we have a pH of 10, pH of 10 is greater than 7, that means we're dealing with a solution that's basic. Now, what about pOH? So recall that pH plus pOH is equal to 14. Well, if we know that, and we've already calculated that pH is equal to 10, then 10 plus pOH is equal to 14, and therefore pOH has to be 4. Finally, to determine the concentration of hydroxide, recall that 1 times 10 to the minus 14 is equal to concentration of H plus times the concentration of hydroxide. Well, we know the concentration of H plus, that's given here. That was the number we started with. So if we plug that in, then all we need to do is solve for hydroxide, and we get that the concentration of hydroxide is 1 times 10 to the minus 4 molar. And you could have done these in any order. It doesn't really matter. Just those are the three answers that you should get. pOH of 4, hydroxide concentration of 1 times 10 to the minus 4 molar, and the solution is basic. All right, question 6. We have a solution that is 0.020 molar HCl. What is the pH? Well, the problem is, for pH, we need to know the concentration of H+, not HCl. But recall, HCl is a good example of a strong acid. So we know that in water, HCl will dissociate into H+ and Cl-. And so however many moles of HCl we have will be equal to the number of moles of H+. Why? Because if you look at the stoichiometry, it's 1 mole of HCl makes 1 mole of hydrogen ions and 1 mole of chloride ions. So if we have 0.020 molar HCl, we would get the exact same thing for hydrogen ions. And this would be the case for any strong acid. What about for a weak acid? Weak acids, it turns out, are a lot more complicated, and that's something that we'll get to later on. But because this is a strong acid, we can just say the pH is the negative log of the number we just found, 0.020 molar, and if we calculate that, we get a pH of 1.70. All right, question 7, we have an amount of hydroxide, and we're adding it to water, and we want to know what the pH is. So if you think about this, this is a very, very small amount of hydroxide, 170 milligrams. dissolved in a liter of water. Let's see what that does though. Now, before we can calculate pH, we need molarity. So we're going to have to convert our 170 milligrams of hydroxide to grams. And we do that by dividing by 1,000. And then, using the molar mass of hydroxide, we can convert that to moles. So 1 mole of hydroxide has a mass of 17 grams. So we have here 0.01 moles of hydroxide. Now, from here, we need the concentration of hydroxide. That should be easy to calculate, especially because we're in 1 liter of water. So we just take the number of moles we just found and divide that by the number of liters. All right, so now we've gone from milligrams of hydroxide to grams, grams to moles, and moles to molarity. So now I'm going to find the pOH. I'm going to do that because we have the concentration of hydroxide. So the pOH is equal to the negative log of the concentration of hydroxide, which is the negative log of 0.01 molar, and that's equal to 2. pH, remember, is pH plus pOH is equal to 14. So we can say that pH is equal to 14 minus pOH. We just determined the pOH to be 2. So we can say 14 minus 2 gives us our pH, or 12. All right, and finally, question 8. This is something we'll get to in a little bit, but I'm going to go over it here anyway. So we have lactic acid has a pKa of 3.86. In our bodies, we typically have a pH of around 7.4. So what would be predominant? Would it be the lactic acid itself or lactate, which is the conjugate base of lactic acid? Now, what we'll go over in much greater detail when we get to buffers is here. The key is that the pH of the solution is greater than the pKa. And if that's the case, then the proton will be removed and lactate will be the dominant form. But again, that's something we're going to cover later on in this chapter.